Okay. Now, having seen that, let's do a few things in a more quantitative way. I'm sorry, I have to plug in this thing. Okay. Now, what you do in a more quantitative way is the following. You would like to have a metric, a measure of conservation, correct? And that is what is called the Shannon entropy. So it is the entropy means disorder. Something will be disordered if it varies a lot, right? Or if a given row is fully conserved, it's not varying, right? And when it's not varying, the entropy is going to be low. So we calculate this quantity, which is the probability of observing amino acid type X at position I. Okay? So for each position, we calculate a Shannon entropy. Let's do it for that position. Now, we are summing up over all different types of amino acids, X from 1 to 20 for position I. Okay? Now, what is here, the probability of amino acid type 1? Type 1, let's say, is alanine. What is its probability? 0, right? There is no. Or what is the probability of threonine? 0, etc. The only thing here we have is valine, whose probability is 1. So all the zeros will be eliminated in the summation. And only we're going to have the valine with probability 1. And the Shannon entropy is going to be 0. Okay. 0 means it is really, there is 0 disorder, 0 variability, fully conserved. Okay. And you can do the same thing for every single every single position I. So here you see you will have 2 entries in this overall summation of 20, etc. So for each column, you have a matrix of conservation. This is a very classical expression that's also used in physical chemistry for calculating entropy. It turns out that the same concept is valid in this type of statistical analysis. So far, so good. Now, we are talking about correlated mutations. This pair, as we have discussed, is correlated. Now, we are doing something else. We are moving from, these are singlet probabilities. These are doublet, okay, pairs. So what does this quantity mean? Pxiyj. The probability of jointly observing amino acid X at position I, Y at position J. So probability of jointly observing amino acid, let's say R, arginine, at position I, and aspartic acid, glutamic acid, at position I plus 5. Okay? So the X and Y stand, again, they vary over 20 different possibilities. Actually, it's going to be 21. Because 21 will be a deletion. When you align, you may have some insertions, deletions, some positions may be blank. So we will also count this as a possible incidence. So normally it's not from 1 to 20, but to 21, counting the deletion. But let's stick to this simple case where we don't have deletions. So this is the joint probability, and we are dividing by the product of singlet probabilities. The probability of having X at position I and Y at position J, because we would like to see how much the joint probability deviates from the product of singlet probabilities. This is when the joint probability is independent. If any variation here is independent of variations there, normally, then the joint probability will be equal to that, and the log of 1 is going to be 0. Okay. And we weight each of them. This serves as a weighting factor, okay? So does the mutual information definition make sense to you? It should, right? It's a measure of the departure from the random probability. So for each column, you have a certain probability of each type of amino acid. And the joint probabilities they may or may not differ from that independent values. And to the extent that they differ, to the extent that this probability is higher than that one, you have more information, more mutual information. You have a higher signal. This means they are co-evolving those. So you note that you have those values for the sites, for the position I, position J. So we are not worried about, we don't talk about the amino acid identity in the output. It's all about the site, okay? Each position, sequence position. Well, this is all you need, actually, to know the basic theory. Now we are going to elaborate a little bit more. The thing is, there are sometimes noise contributions, and you want to minimize the noise, and you want to have some sort of reference states, basis state. One correction to the mutual information, which is called MIP, introduced in 2008, was to subtract this average product correction. It's called average product correction. So what this says, the average product correction is like an average over all elements. Average, we calculated the mutual information. I was the mutual information. You evaluate the average over all elements. And this is the average over each column and each row. So this is a normalization term, if you like, a subtraction to eliminate some artifacts, if you like. So that proved to be more accurate than MI, the original mutual information. I don't want to elaborate on that, but the thing is that in your evol module of ProD, you have the possibility of doing calculations of selecting whichever methodology you like. You can select the mutual information directly, or you can select what's called the modified mutual information or corrected mutual information, or other methods. And I'm not going to go into other methods. Now, I would like just to give you a few highlights, show you how these things are useful. To mention a study of a former student of mine who contributed to this component. So what Ying did was the following. Ying took a series of HIV protease sequences. These are from humans, okay? Different strains. And we have two classes. Stanford is accumulating a database of HIV protease, different strains. So we have patients who have been subjected to some drug treatment, and other patients who have not been yet treated. Okay? And these are all being combined together and analyzed. And the idea is to compare, their genome, whether some mutations are more frequent in one group versus the other. How does the effect of drug treatment affect, if any, the sequence evolution? Okay? So from those, if you analyze everything, this is the methodology. You analyze all the sequences for HIV protease, and now you have this matrix, mutual information, which you can fill in. Okay, it's usually kind of a sparse matrix. Of course, you can't see much, but the darker spots are stronger signals, lighter spots are weaker signals, and in many places there is no co-evolution. Okay. Then to kind of better visualize what is happening, you can do some kind of clustering analysis. So what you do is you shuffle. Oh, this is Ying, by the way. In all photos that we took during his tenure in my lab, he always does that. He liked to do that, Ying. He was really extremely smart. And anyway, he did this type of spectral clustering where you are shuffling rows and columns to organize them in a better way, and to such that you obtain your sparse matrix now has some entries that are collected together. Okay, so these entries that are collected together, it's amazing. These are where the coevolution signals are strongest. Okay, So here the residues were indexed from 1, 2, 3, 4, 5 to n, okay? Here they are like 1, 3, 12, etc. They are just shuffled, and in the same order in both the abscissa and ordinate. Okay, he did this analysis twice. Ying did this analysis twice. One with the untreated patients' sequences, and he got this, you see this cluster here. And then he repeated with this second group of strains, and these are all downloadable, from Stanford database, very easy. And then you look at that. He got the same cluster more or less, but he got another cluster here. What is happening? So there are a few new cases where there are mutations. And you remember we mentioned something. There are those drug-resistant mutations. And these turn out when we analyze them. Now, we don't know anything, about the genome or the evolution or what happens. Then we said, oh, these are only observed in those patients that have undergone this type of treatment. And we wanted to examine, so we call these are the phylogenetics. So during evolution, naturally, there are changes and these things happen. And these are regions that apparently sustain some changes in amino acid identity, provided that they are compensated by a correlated change. Okay, so they are not, deleterious or consequential, but these are only observed in the drug in the presence of the treatment. And then we wanted to see where they are located. The phylogenetic cluster are the red ones here. You can see they are more at the exterior regions. And the drug resistance mutations, which we call them, are located at those blue regions. And as a matter of fact, this protease is a dimer. And so the major movement is the movement of the two monomers with respect to each other. And to block this type of functionality, drugs are being bound at the interface between the two dimers, especially at this region. So what the molecule is doing is simply, creating new mutations at the vicinity of potential drug binding sites. Then we did our A&M analysis, elastic network model analysis. Here is the big surprise, or maybe not surprise, because we can have some intuition. When you do the mobility profile, when you calculate, you remember I explained yesterday the mobilities. These regions are the most flexible regions, most mobile, this color-coded diagram. And my laser pointer is becoming weaker and weaker. Can you see it? Okay, I hardly see it. Okay. And this region, look at the similarity. So these are the most constrained regions, and these are the most flexible. Red are the most flexible regions. So the molecule is so smart. It is doing the mutations at sites that are very constrained. If it were doing mutations at those positions, it would not, affect the functionality. It is those regions that are highly constrained, which we are actually targeting with the drugs. Drugs usually bind here. And this is in their vicinity that the most constrained regions that are also being undergoing those drug resistance mutations. Isn't it fascinating? I thought this was really something very striking. Anyway, this was, now this gives us new hints about, this one is better? Okay, thank you. But now I need to use both. Okay, so this gives us new hints. What is it? Well, we have an idea about the regions, that are highly constrained based on our elastic network analysis, are not going to easily tolerate mutations. If there are mutations at those positions, they are likely to be consequential. Okay? And then this drove us to do, well, this is a summary of what was reported there. Two groups of mutations, exposed phylogenetic on the mobile regions, and the multi-drug resistant mutations at the dimerization interface, which is dynamically very restrained. Now these, of course, the way we always make progress is by asking the right questions. Not necessarily the right answers, but the right questions are very important. So you have, now we are starting to say, are those key mechanical sites, we call it the hinges, are they conserved throughout evolution? So we usually think of the catalytic site, the chemically active site, to be conserved. But do we also worry about the mechanics, the hinges? Or is there a correlation? Can we have observe a correlation between sequence variability and structural dynamics? And actually, this is practically the title of an NIH grant that I have. So this is what we are exploring. And how does the structure ensure that substrate specificity and conformational adaptability? You have conformational, you need to be somehow flexible, right? To accommodate the binding of substrate. But you cannot be so flexible. You want also to be somehow specific. So this specificity is conferred by sequence variations, and adaptability is conferred by dynamics. So there is an interplay between the two things. So what we did then was to do a systematic study, now that we have some insights. So here is the systematic study. We take a query enzyme, and this is what Evol is doing. Now you have the sequence, and from multiple sequence alignments, now we have the sequence. Here are the insertions. You see the blanks. So we PFAM database, protein family database. We obtain for a given query sequence, we obtain the family of the multiple sequence alignment on the one hand. And on the other, I can't use 2 minutes. And on the other, we have, I'm sorry, too fast. We have the structure from the PDB. Okay. Then next, we do this, after this multiple sequence alignment is being refined, and you don't need to worry about the details. The program does these things. Now you have a better subset of sequences from which you can extract more accurate information. And then we do our calculations, basically 2 types of calculations. One is to observe what are the conserved sites, the entropy, and then the other one to obtain this type of maps for mutual information, co-evolving sites. Are you with me? Did I lose you? So we do the same thing actually here. Look at the similarities. We have the mobility curve and also the cross correlations in the movements. So the protein may have correlated movements. The protein may have co-evolving amino acids. How do this? So these are 2 totally different maps, providing measure of the correlations in sequence evolution or in the dynamics. How do they correlate? Or the mobility. Now, what is the hypothesis? The hypothesis, it's important sometimes to have a hypothesis, even if it proves wrong at the end. The hypothesis is that if you have a very constrained region, that region ought to be conserved. And a very flexible region, a very mobile region, may tolerate mutations. Otherwise, the functionality will be disrupted, right? And that is how we have been comparing the the conservation versus mobility, coevolution versus covariation dynamics. And now we did for a bunch of enzymes. We want to, because when you observe one enzyme, it may be extremely misleading. We had to do it with a large data set to get statistically reliable results. And that was actually published in a very prestigious journal in the field, and led to Evolve, to building Evolve here in our Prodi software, which you are going to learn. I want to go a little bit faster, but still this example is not bad. So these are what we obtain. Don't worry about the scale. We don't worry too much about absolute values. We are more interested in profiles, in understanding the behavior. So this is the mobility profile based on a subset of most collective modes, which we call global modes or slow modes. And if we take everything, this is the black profile. And actually, everything is shifted vertically just to provide a clear visualization. So the absolute value doesn't matter, the profile. This is what we obtained from the elastic network model analysis, and this is what we obtained from the sequence entropy. And can you see that there is a correlation? It's not so bad, you see. So what happens, the entropy is high. High entropy means sequentially disordered, okay? Low entropy means conserved. So the minima here, low entropy regions, are also physically, they have less mobility. Are you with me? That's a very important observation. That, you know, that in a sense, sequence variability throughout evolution and the dynamic, you know, physical conformational variability, they go hand in hand. And you can have the same vice versa. Okay, that one doesn't work. So now we have this type of plots. Actually, you can go, you can see more directly how when the information entropy, and these are for each point here represents you know, the results from multiple proteins. Like, so you can see that the information entropy essentially increases with effective mobility. Don't worry about the details, two different types of subsets of modes, but suppose we take all the modes, the blue curve. The blue curve is all the modes. You can see the trend. If you focus on the most global modes, the slowest, which are, you know, the most cooperative, if you extract that and filter out the rest, you can see this effect even in a more pronounced way. So that completes this section, practically. Oh, here are a few, you know, nice examples to have more fun. Doesn't seem to work, but that's okay. So the idea is, one may argue that, oh, okay, hinge sites, which we observe to be conserved, they may be conserved because they are buried in the structure somewhere, you know, deep in the middle, something. But then we have seen that those the hinge sites in many cases are conserved and not necessarily buried. You know, they can be located anywhere. So this hinge site, for example, which provides the motion of this helical hairpin with respect to the rest, is highly conserved. Or there are these are the hinge sites between the two subdomains of this protein, which are highly conserved, etc. So each. And what was colored in different colors was which they are at the interface of these portions of the structure. For example, these residues are at the interface between this green segment and the violet segment. And there is a relative movement of each of them with respect to each other. And these things at sequentially at the interface are highly conserved. And they are very, of course, serve as hinge points. All right, another concept is, let me ask you. Now you think of some antigen-antibody binding. You know, you have, suppose you have a molecule that binds many different substrates, okay? There is a recognition site. Not necessarily binding tightly, but the recognition site. And suppose you have an antibody that actually binds, you know what they call those loops. They call them hypervariable loops, the things that bind different substrate. Why do they call them hypervariable loops? They are hypervariable actually sequentially. You know, the immunoglobulins, they have this Y-shaped structure, and at the tip you have those highly variable loops, sequentially hypervariable. But when you do the analysis, and this was one of the first systems we studied, these regions are very flexible. I saw in one of the Nature issues in the last couple of weeks, the title is Why? So Y is Y, you know, the cause. Y is the Y-shaped. That So there is a reason for the molecule to have a Y shape, because that allows from, there is a solid base, and then it allows from some sampling of the space, the upper parts of the Y. And so the whole point is that those hypervariable loops that are sequentially variable are also very conformationally mobile. These two things they go together, or in the same ways as hinge sites are conserved, the regions that are sequentially very variable are very mobile, okay? The opposite situation. More than that, these regions that are hypervariable, they vary to confer specificity, because they bind different types of antigens. They bind different types of substrates, okay? So the recognition sites for such molecules have usually co-evolving amino acids. They change, but they cannot change randomly because they still need to maintain a specificity, so they co-evolve. These are important concepts, and maybe it's too much at this time, but the idea was that when we observe co-evolutionary trends, and then we see some strong signals, these signals would be actually usually located at the binding sites of substrates. Here, in this case, we have this region of residues that interact with DNA that co-vary for improving specificity. Or another example. So you have this molecule and its substrate, and substrate is the blue, and this region near the substrate is calculated to be the most flexible part of this molecule, as the peak here demonstrates. So these red residues are all here. It's the most flexible region, but also it has a role. It is just mediating the binding of substrate. It's assisting. So the regions that co-evolve strongly may have a role. They vary because they are to confer specificity for substrate binding, and they enjoy extended mobility. So this is like a summary of everything that we have observed so far. Chemical sites will have minimal mobility. They will be highly conserved. Catalytic sites, and they need to be high fidelity. Precision is essential for their functionality. Core residues, in the protein core, they have minimal mobility. They are conserved because they have to be conferring the high stability. Hinge sites, they have minimal mobility. They are conserved, although they have this rotational flexibility, but they are fixed in space, okay? And the substrate recognition sites, they move a lot. They show some high coevolution propensities, and their dominant feature is adaptability. Finish. So the conclusion, just summarizing everything, and I know that you want to go inside to the next, is proteins are designed to favor functional changes in the structure. Pre-existing soft modes facilitate those functions. And the collective mechanics are, enabled by conserved residues. There is an enhanced flexibility at the recognition sites. Correlated mutations at recognition sites also help with substrate specificity while conferring conformational adaptability. And inclusion of, considering dynamics is essential for druggability assessment. One last slide, which is my favorite. I did it 15 years ago, but it still is valid. So I have been talking about chemistry and mechanics. You could have called this, instead of mechanics, you could call physics if you like. But there is you've seen probably in the literature, biomolecules are mechanochemical entities, things like that. So there is an interplay between mechanics and chemistry, right? And so when the thing is, the idea is the following. We have a bunch of systems ranging from a small molecule to large complexes, okay? From 10 residues to 10,000, 100,000 of residues, composed of a small fragment, one protein, multiple proteins, hundreds of proteins. So what am I going to say? What I'm going to say is that at this scale, when you look at small systems, what is more important, chemistry or mechanics? Chemistry. Chemistry is important. As you know, you have increased specificity, and the chemistry is really important. You have to put in all the details, even quantum mechanical, quantum chemical. Not mechanical, chemical. But then if you go in the opposite direction, gradually, the features, the chemical features become less and less important. You have the overall architecture that matters and the overall mechanics. So I would submit that the elastic network models are mostly, and they are purely, mechanical entities. There's no chemistry in them, are more applicable to this scale in general, although they help us a lot, even at the level of single molecules. But ideally, and also in a very useful way, that's where we want to apply them. And when you do simulations, when you explore smaller systems, you do just full atomic, and you take account of the full chemical entities. I think we discussed enough. So these are, again, I will finish with Ahmet and Anindita. Ahmet was phenomenal. I think he was really phenomenal. And Anindita was also extremely smart and nice at the same time. Of course, you know these people now. You know my former student. Mao has been around, and he will continue to be around. He's amazing. I'm very lucky to have him as my visiting scholar from Tsinghua University. And then Indira, of course, she's waiting. She's becoming impatient now. Last but not least, we want to thank Marcus. Where is Marcus? A big applause to because he is the driving power behind all this effort. We could not do anything without him. And I have to do that also. So thank you very much. So you're ready to move to the other room. If you need a break, 5 minutes, that's fine. But I think I'm sure you are very impatient to apply these things, right, to see the application. Okay. Oh, okay, 10 minutes, 10 minutes. Let's have a break of 10 minutes.